View of my backpack. Awesome. All right, let's see what happens. No, I don't want too many. Shoop. All right. We're back. So, anything else from homework or anything else before we get into new stuff? What's happening Monday? Quiz, right? I'm sure there's other things happening Monday. For us, there's definitely a quiz on what? Chapter 11. All of it. All right. So there's no questions. Any other questions? We're going to get into chapter 12. 12. Holy shit. Done. Almost 12 chapters. Not quite 12. Just skip 9. Alright, so the idea here is, and let me, it's freak me out, just looking for my camera. Let me give you a couple of easy examples here, and this should sound familiar, this idea. Can you guys tell me what the next element is in that series, in that sequence? Or can you hear me? Yeah, why? Is it possible that there's another pattern? Yes, good. It's totally possible. Another pattern that might exist is probably going to be something very complicated. Right? So normally what's intended is the most obvious pattern. You guys kind of with me? Yeah. So if I give like 4 elements, that's normally enough to determine what the hell I mean. Right? What about this here? Think about times -3. I didn't ask for that. What's the next term? Dave's like, dude, I gave you what you need.
Times 3.
162. All right. Okay, sweet. So the idea here was I added 3. The idea here is I multiply by -3. Cool. Right? And in general, we actually call this, we normally give this the letter D. Why would we call that D? Yeah, it's crazy. 4 minus 1 is 3, 7 minus 4 is 3. It's the common difference. And we normally give this one the letter R, just to cut you guys off if you thought it was going to be M. It's the same idea as this. I take the difference to figure out what was added. I take the ratio to figure out what was multiplied. So that's why it's called R, the common ratio. You guys still kind of with me? So section 12.2 actually focuses entirely on this kind of sequence. And this is called an arithmetic sequence. Arithmetic, it's nice, it starts with the letter A. So that's where you add the same thing. So you can add negative, of course, and have it decreasing. Cool. And this one is called a, what do we know this called? Geometric. Good. Geometric. Geometric, unfortunately, starts with the letter G. But it's where you multiply by the same thing, of course. Right? Silent G. All right, that's not too bad, right? So we're going to focus on those in those sections. There's another type, there's a million different types of sequences. In fact, there's a whole website, believe it or not, devoted to cataloging sequences and talking about their properties. All right, so there's kind of a famous one. And of course, famous in mathematics does not necessarily translate to the general world. But has anybody ever seen Fibonacci? Look at that. You guys knew where I was going. What's the next term in that sequence?
21.
Yeah, 21. What's the pattern? Add these 2 to get this guy, add these 2 to get this, and of course add these 2 to get this guy, right? Every one is the sum of the ones preceding it. So in order to even start this sequence, somebody has to give me 2 numbers. So this is the Fibonacci sequence, but you could also have something like this, 7, 9, and what would the next number be? So I want it to be Fibonacci-like, 16, and so forth. Now here, take a second to do this, because I don't know how many of you guys know this. This is 21. Find the next 4 elements. And then find the next 6 elements for that. Take a minute and just do that. Right. I just want you to be busy for a minute. Now, I got a point to this, hopefully. Is that right? Yes. If I would have gotten that one wrong, that would have sucked. This one I kind of know a little bit better. Cool. Now do this for me. What's 144 divided by 89? So I've taken that one divided by the one before.
1.62.
Don't round it so much. Take me a few more.
0.6179.
Alright, I like it. Cool. And then what happens when you take 280 divided by 173? See if I went far enough out in this one.
The same. 1.618.
1.618.
49.
Blah, blah, blah. Yeah, so they both are basically 1.618, right? Is that number familiar to anybody? I mean, those of you who knew the Fibonacci sequence, did you know about this? That if you go far enough out, the ratios of one term by, take one term divided by the one before it, that's going to approach this number. It actually approaches, this exactly is 1 plus rad 5 over 2. You can try in your calculator if you want to. And to tell you honestly, it's really cool. Part of me wants to take you down this path, but the other part reminds me this is not really our curriculum. I don't want to freak the hell out of you. But you can actually set up a polynomial. It would be a cubic equation that defines this, that captures this rule, solve it, and that's going to be one of your solutions. And you do actually get other solutions, which then you're like, well, what do these other solutions mean? That gets interesting. So anybody know what that's called? That little deal?
Golden ratio.
Sweet. It's the golden ratio. So that's the golden ratio, because when people found out about it, they thought it came from God. And so they call it the golden ratio. And they got the golden rectangle, right? I don't know if anybody's going too far with that, but golden rectangle is one where, for example, note cards that you guys use, how big are they?
3 by 5.
3 by 5, 3 by 5, or 5 by 8, 5 by 8, right? A widescreen TV is in what ratio? 16 to 9. What's 16 divided by 9?
10.6.
It's close, right?
1.7-ish.
I think it's 1.66.
1.7.
Maybe more. I got
1.777. Yeah.
Really? I'm close, sorry. I can live with that. 777. Roughly. It's close, right? And then just to say the last thing about, well, Fibonacci sequence you can spend a freaking lifetime studying. It's insane. And I'm actually right now doing some research. This is only one golden number. So if you know anything about golden numbers, I think I said something like this before. This is only one of them. There's an infinite number of golden numbers. And this one kind of relates to the division of sides of a rectangle. The other golden numbers relate to the division of, for example, diagonals. If I divide two diagonals from some more-sided figure, that they're related to those. It gets really neat. All that shit you don't have to worry about. It's not going to be on the test or anything. It's just interesting stuff to know. Right? So what I'm trying to do is figure out. So there's actually a trig function. Believe it or not, there's a trig based function that gives you the values. And I was curious because I learned about that, and now I was saying, well, are there any series? Do we know if there's a series that leads to those values? So I've discovered 3 so far that leads to 3 of the golden numbers, and I'm trying to develop a general rule for them. Right? This is a little bit arduous to go through to make them. Anyway, all that stuff's on the side. Just to let you know that, sometimes I actually get time to play around with this shit too. Alright. So let's step back into what we're going to be interested in. They do talk a little bit about Fibonacci sequence in the book. I can't stop talking about it. It's too bad for you. So Fibonacci sequence has to do with one of the more interesting ones is like the trees, how many branches there are. And the book has a much better picture than I could ever hope to make. But if you go up and you count the number of branches, there's 1, there's 2, there's 3 there. So there's a picture in the book that shows you as you go up. So if it's a tree that nobody's cut and that has grown normally, right? Didn't have any weirdness happening. Didn't have some creatures gnawing at it or something, right? Then a lot of trees follow this Fibonacci sequence. So this purely mathematical playing around with numbers directly relates to nature, because nature very often grows off of itself, right? So there's a chambered nautilus, which technically doesn't really follow this exactly, but it's pretty close. And as the chambered nautilus grows, it grows its shell. And then it grows its shell some more, and it grows its shell some more, and you get this neat spiral effect. And it actually is based off the Fibonacci sequence, roughly. Right? So it has to do with how nature grows on top of itself. Yes?
So is that the golden spiral? The spiral effect?
Yes, good. I like it. And it would be, you start with a rectangle and you cut it so that the ratios are correct. And then you made another golden rectangle, and then you cut it, and then you cut it, and then you cut it, and then you make this spiral if you connect all the corners. And again, it's in the book. I can't compete with the book's pictures because they're computer generated. Right? Mine, all you need is somebody with a basic understanding of drawing, and you probably do better than me. Right? Don't need to go to a computer. Okay. But again, that's just one little piece of this. This is not the Fibonacci sequence section. But you can understand why a math geek would kind of want to go off on this, because they've actually done studies that the Fibonacci sequence, for example, if you have a frequency, well, not a frequency, but a harmony, I don't do music really, but when you put 2 frequencies together, if their ratio is close to the golden ratio, then it's a pleasing sound. If not, then it's a jarring sound. Maybe it woke you up this morning. That's something that's way far off from the golden ratio. Visually, we'll pick things. We'll say, that looks better than that. That looks better than that. Normally what we pick has to do with the golden ratio. And it should kind of make sense, because if that sort of describes how nature builds on itself, we will be drawn towards healthy things. You with me so far? We'll be drawn, why would we be biologically drawn towards healthy things? Because then our offspring would have a better chance of survival, right? Or if I see a tree and it looks a little bit misshapen, I'm probably not going to eat its fruit. Something bad has happened to that tree. So I want something in my brain to be automatic. I don't have to think about it. I mean, don't want to, and then they'll find something else, right? A caveman jumped there for a second. You guys semi with me? It's neat. So there is a psychological connection where something aesthetically pleasing very often has something to do with the sequence. It's not magic. It's not anything. It's not math invading anything either. It's just a neat connection between math and some other things. Anyway, all right, that's enough. Is it Jeff? No, one more thing. You could use Fibonacci sequence. A friend of mine, my friend Sean, he's a financial analyst, which basically means he makes a stupid amount of money. So he can do things like this. Through this recession, he made money in the stock market because there's a method using Fibonacci sequence where you look at the number of dips in the stock market, and then if you hit a Fibonacci number of dips, then you either sell or buy dips or peaks. You guys kind of with me? Business and me don't really go along, so I haven't really looked into it that much. But it worked for him. It's crazy. So there's an approach to that. So if you have enough money, then then the old adage is true. If you have money, you can make money. If you don't, that's too damn bad for you. And me, and all of us, most normal people. All right. But he's also got 5 kids now, so his money goes quickly away. All right, so let's bring it back. Sorry. So what you're going to be concerned about, first off, is the difference between a sequence and a series, right? And actually, before that, let's talk about how to find an equation for the nth term of a sequence. So let's come back to this guy. Let's come back to 1, 4, 7, 10, blah, blah, blah. So let me define a couple of things, some symbols. Normally we talk about sequences using the letter A and the letter B if there's a second sequence. So A1 would be the first term in the sequence, so that would be 1. So A2, amazingly enough, would be 4. That's insane. And A3 would be 7, and so forth. Right? So what I'm asking now is, I don't want to have to keep adding frickin' 3 if I want to know what the 873rd sequence element is. We'll add 3, and then add 3, and then add 3, and then, no, screw that. Right? Since there's such a rigid way to get there, there must be a easy, well-defined, dependent on n equation so I can just get the 873rd element quickly, right? So I'm trying to figure out what's an in terms of n. So your first guess might be wrong, which is okay. Who has a guess as to what that might be? I understand. Well, some of you guys sound like you know it, which is good. I have nothing wrong against that. But if you think it would be, why do you think somebody might think it's 3n? Yeah, so, and why does this not work?
Because it's not fun.
Yeah, so if I try it, A1 would be 3 then, according to this. A2 would have to be 6. But notice something interesting, that if this is 3n, gives me 3, 6, 9. What's true about the one I'm working with? It's always what? It's always how much related. Yeah, it's always how much below.
Minus 2.
Yeah, so if I do this, that is the definition. Try it. What's A4 supposed to be?
12. Minus 2.
Who do it? Oh. So A4, if I use this definition, it would be 12 minus 2 is 10, and A4 is 10. Sweet. All right, now let me make it more general for those of you who know the official formula for this kind of thing. I didn't really necessarily want to go here right now, but section 12.2 talks about these, right? But there's a more general approach for arithmetic sequences, which is, what do I keep doing here? How did I get to 4 from 1? 1 plus 3, right? How did I get to 7 from 1?
Plus 6.
1 plus 6, which is twice 3. So this is 1 plus 1, 3. So this is 1 plus 0, 3s. So what is this number? How does it compare to where I am in the sequence? 1 less. So I say I start at 1, and I add 1 less of the common difference. So it's kind of silly. So then this is really telling you how many steps you've taken away from 1. So if I've taken 0 steps, I'm at 1. The minute I take 1 step, which means I would be where? Where do I start? What element do I start at in general? A1. So I haven't taken any steps yet, right? All right, good. So for n equal 1, I have no steps taken. So I start at 1. If I take 1 step, I'm at A2. So that would be 1 plus 2 minus 1. Well, check. Let's do this in general. Put this in here. This is actually 3 for this dude, right? So if I start at 1, if I take 1 step, I'm now at A2. A2 would be 1 plus 2 minus 1 is 1, because I've taken 1 step, times 3, which is 4. It makes it, and you're all like, man, Jeff, you just added 3 and you just made the whole damn thing so difficult. What's wrong with you? But just to show you, we get the same thing we got here. Because do you think it's always easy to do what we did here? No, it's probably not always easy, right? It actually kind of is for arithmetic, but we'll go past it. I'm trying to show you a more general thing. So, what do I get here if I simplify this? 3n minus 3 plus 1 is 3n minus 2, which is what we got just by observation, right? Let that soak in for a second. So again, this is going to be an equation from section 12.2. What I wanted to focus on today is no matter what the sequence is, I can try to, by observation, try to come up with a definition for that sequence. So if I wanted the 837th element, I just plug 837 in. Much better than actually having to count that far out. Okay. So what about, let's see. Here we go. Here's one for you. Can you do it in your head, Jeff? We'll find out, Jeff. What are you trying to do? I don't know. Do something for myself. Yeah, alright. You can do that, Jeff. That'll be. I have faith in you, Jeff. So now I want to figure out what AN is. So one approach to this is to write down A1 is 1/2, A2 is 3/4, and then try to figure out how are the numbers that are in here dependent on that number, right? Because I'm trying to figure out, based on N, what is that element? So I want to figure out how are they related to their position in the sequence. The bottom should be relatively easy to figure out. What's happening with the denominator every time? So how can I write that in general? Because then, if it was 2n, then this one should be 6. So it's not 2 times n.
2n squared. No.
2, 4, 8, 16. When n is, I circled this one. When n is 1, I get 2. When n is 2, I get 4. When n is 3, I get 8.
2 squared.
2 squared is 4. 2 cubed is 8. So in general, it's 2 to the n. Kick ass. I like it. I like it. This is our first baby steps into this thing. And it's weird when you start doing this. You don't know what you're allowed to even try to use. You're allowed to try to use any damn thing. Which is almost bad, because then you're like, well, shit, it could be anything. And sure enough, you get far enough along in this topic, and you get to the point where it's really not easy. Some of these could have been reduced, for example, and you got to figure out what would it reduce from so I can actually see what the formula is. Do you guys kind of follow me? This can get to the point where it drives you insane. I'm going to try to not let that happen, because we're just starting to get into this, right? What about the top now? Did I do that right, Jeff? You're an idiot.
13 over 32.
What was I trying to do? I forgot now. Oh yeah, that's what I was trying to do. Well, that should be a 5. No, this is a 3. Why am I having so much trouble with this today?
That's the same thing you put.
Yeah, I know. Thank you for that. Oh, I see what's happening. Okay, amazing. So let's see. 2. So that's a 5. Let's see. This is a. Oh, you just call it 7. I think, right? Good Lord, Jeff, what is that? That is a 9. So what are you looking at wrong here? Oh, A1. I see what I'm doing. All right. So what's hard for me is in this book, they always start at 1, which is kind of subtle. And really, if you think about it, that's why this equation looks so ugly, to be honest. It's because I took one less step than where I am. So really, it would make the most sense if I started not at A1, but I started at A0, because I haven't moved at all. And then this equation would be nice. It would be 1 plus 3n. You wouldn't have to do the n minus 1 little shift, right? So my brain was kind of forgetting where the hell I was. So the bottom is cool, and the top is now a little bit easier, right? Yes, cool. In fact, this is a general way to write any odd number, either 2n plus 1 or 2n minus 1. All right, cool. I like it. So these are the right numbers. Okay. So odd numbers, 2n plus 1 or 2n minus 1. What about if it's, let's do this. Here's the next kind of level of this. What if it was something like, let's keep it simple, Jeff. Yeah, let's just do this one together. 2, negative 6, 18, negative 54. So what aspect of this sequence do I have to capture that we didn't have before? Sign is changing for each one. Holy shit, how the hell am I going to do that? But we've identified what's going on here.
Negative.
Yeah, it seems to be multiplied by negative 3 every time, right? So A1 is 2, A2 is negative 6, which is how related to 2? 2 times negative 3, right? And A3 is 18, which is how related to 2? 2 times negative 3 squared. So what's this really? 2 times negative 3 to the? 0, because I got none of them, right? And again, there's that whole thing. If only I would have called this A0, I wouldn't have this weirdness. Do you see how these are off by 1? This is 1 here. They're off by 1 because we started at A1. If only we would have started at A0, it would be better. So when you get further along and you have these sequences in series, you can choose where to start, then you choose the better place to start. You start at 0. So what's the general form then?
2 times negative 3 squared.
Yeah, the beautiful thing is what stays the same every time. 2 times negative 3, 2 times negative 3. The only thing that changes is the power. N minus 1, exactly. So when I'm at 1, this is supposed to be 1 minus 1, 0. When I'm at 2, it's 2 minus 1, 1. So when I'm at n, it's n minus 1. Why does that formula tell me it's going to alternate signs? How did I capture that?
Like on the negative and power and
The exponent.
Yes, yes. So negative 3 to the even power is going to be positive. Negative 2 to the odd power is going to be negative. So therefore, it's going to switch signs between. I like it. So if I had a very simple problem like this, you can do it, Jeff. There it is. The only hard part about that is the negative part. All right, you guys, I'll do the top. Yay. But how can I capture the negative part? Let's capture that too at the same time. So the first one has to come out positive. So when n is 1, it's supposed to come out positive. So why is that not going to, or is that going to work?
No.
Because then when n is 1, this will be negative. So then I just make it minus 1 or plus 1, kick ass. It just has to be offset by 1. Let me stop there for a second. Does that by itself make sense? This is in general how you take care of the alternating part of a sequence. And what's going to be the bottom? Every time it's how related. So A1 is 1/2. A2 is 1/3. So the bottom is going to be n plus 1. When the n is 1, 1 plus 1 is 2. All right. There we go. I like it. I like it. So that's the first skill to realize you need to develop, is how to write an based on what you're given. Let's look at something like the Fibonacci sequence. This will introduce something kind of new, because the Fibonacci sequence is not based off of some external thing. It's actually based on itself, right? So this is based off the external idea of negative 3. I don't see negative 3 in there anywhere, but I just keep multiplying by negative 3. The other one is I kept adding 3. They're based off of something external. Does that make sense if I say it like that? I've actually never said it like that, but it sort of makes sense to me. All right. So this is based off of internal things. Whatever's in the sequence makes the next term. So in this case, A3 equals what? Don't say 2. A3, how did I get 2?
A1 plus A2.
Beautiful. A1 plus A2. A4 would be
A2 plus A3.
A2 plus A3. That's crazy. So what's AN plus 1? I might make it easier too. Or I don't know if that's easier. We just call it AN. We'll just do AN. What's AN going to be? an minus 2 plus
And
an minus 1. Good. To get the fifth element, I need to take the third one plus the fourth one. The one that was 2 before it and the one that was 1 before it. They go together to make it. Are you with me? Or are you against me? Alright. And so can you imagine? I want you to imagine. You can make other sequences that are not Fibonacci, but they use this kind of thing. And those sequences, based on its own elements, that idea. To make the next one, you base it off of what's already there. So you need what sometimes is called seeds to get started. So 1 and 1 were seeds. And then I grew from there. Right? Aww. Whatever you want to use. But this, in general, this is called a recursive definition. Recursive sounds like you sign on that stupid little pad and you had to clear it because it looks nothing like your name. You had to recursive. But no, recursive, recursion in general just means it's kind of building on itself. I like it. I like it. So let me give you this. Let me give you this. I should probably just do the handout. Yeah, let's do this. I want you guys to try the top part of this because we haven't talked about the bottom part yet. Don't worry about that. We'll do it. So do the exercises 1 and 2 up here. You can read the bottom if you want to.
a copy of the answer key for that thing from yesterday? You came in a little late today.
Got that one earlier, so. All right, let's start looking at these here. What do you get? This first one's pretty simple, right? Just got to find the first four terms. What do you get? 1? That's great.
1/3, 1/4.
Awesome. All right, so in A1, you plug a 1 in, A2, you plug a 2 in. So it's almost like f of n, but since it's a sequence, we give it its own sort of notation. Right? So it really is just a function of n. This guy is almost the same, really. What do you get here?
1/4.
1/4.
2/5.
2/5.
1/3.
1/2.
Good, because it would be 3/6, which is 1/2. I like it.
4/7.
4/7. And see, that's the kind of evilness. Now, if I didn't give you that and said find these, you'd have to realize that that's got to go back up to 3/6. It's not difficult to see it here, but yeah, it could be very, very difficult to see it other places. And then this guy's kind of nifty. What's A1?
1/2.
Yeah, because it'll be 1 plus -1/2 to the first, so 1 minus 1/2. What's A2?
5/4.
Yeah, it'll be 1 plus 1/4, because it'll be -1/2 squared, so 1 plus 1/4 is 5/4.
7/8.
Yeah, it'll be 1 minus 1/8, so 7/8.
And 17/16.
Yeah, so 1 plus, where am I at? 16, 1/16, 1 plus 1/16 is 17/16. Cool. Which looks a little bit like that one, right? Not quite, but almost. What about B? This one shouldn't be too evil. Oh, yeah.
Or well, n plus 2 over n plus
I like it. N plus 2, and the bottom is 1 more than that, so n plus 3. And what's the limit as n goes to infinity of this? What situation am I in? Whenever I have a ratio of polynomials, I can look at it like a horizontal asymptote idea. Remember that, especially those who are going into Calc 1 and Calc 2. Both of those use this idea a lot. So the limit's going to be 1. And look, does that make sense? 3/4 is 0.75. 4/5 is 0.8. 5, 6 is 0.833, I think. 6, 7 is out of but it's closer to 1.
It's getting close to 1 with our region.
So then this will be 1. Now here, the trick to this one is, notice, before you even get anything specific, how does the top relate to the bottom? The top is always 1 less. So then you say, oh good, I only have to find the bottom, because then I automatically have the top. It's just blah minus 1. Do you see that? So that's sort of like an overarching thing you look for first, so you know exactly how much work you got to do. I got no work for the top. All my work is on the denominator. So how do I write the denominator? Yeah, we saw that one before, right? 2 to the n. So then the top is going to be 2 to the n minus 1. What's the limit? I like this one.
1.
Now from the sequence, it looks like it's going to be 1. Right? But if you get into my Calc 2 class and you try to tell me, observation, no, screw that. You can't observe a damn thing and prove anything with it. But it looks like it's pretty much going to be 1. But here's the way to do it. You ready? Because we don't know, man. Just do it. This is not the same as this, is it? No, they're not. It's not polynomials in there anymore. But I can do it exactly the same way. I can divide by 2 to the n. Get out of there, Jeff. 2 to the n divided by 1, 2 to the n is 1. 1 divided by 2 to the n is that. 2 to the n divided by 2 to the n is 1. You guys remember this? Because here I could have divided by n, but why don't we do that? Because that's crap. We know the shortcut now. Right? But for other things, I pretty much have to do it. And when n gets really big, what happens to this guy? It's stupid small, quick. So that limit is 1. Cool, that's the proof. You don't have to do that here again, because that whole limit idea is a preview of calculus for you guys. But we use the idea here, that's why I want to show you this.
That's also an alternate answer to it. It's 1 minus 1.
Beautiful, I love it. Because this guy looks a lot like this guy does, right?
Yeah.
So this one was alternating. It was over 1, under 1. Over 1, do you guys see that? But this guy was always under 1. So that's why you can actually write 1 minus 1/2 to the n power. That kicks ass. So 1 minus 1 over 2 to the n, that's another way to do an. Sweet. Yes?
You start always at a to the 0, or do you have to specify?
In general, for this class, and actually in general, to be honest, in general, n, the reason we use n is because it comes from the natural numbers. And I don't know if you guys remember, the natural numbers start where? At 1. Whole numbers, appropriately named because they added a number that looks like a freaking whole. That's the whole numbers. They start at 0. Natural numbers start at 1. That's where the n comes from. But when you're defining your own sequences, you just define it the best way, which very often is not freaking starting at 1. I like it. Alright, good. And then a little quick thing here, and this is what I was saying earlier, these are sequences we're working on. Sequences are numbers separated by commas. So sequences are just lists of numbers. When you start adding those elements up, that's when you call it a series. So a sequence is just a list of numbers. A series is that same list added up. So here, let me just blow your mind a little bit and then we'll call it a day. Can anybody imagine a sequence of numbers? Infinitely long, right? This is an infinitely long sequence of numbers. What do you think is going to happen when you add them up? So for example, 1, 2, 3, 4. That's the simplest sequence ever. What's going to happen when you add all of those up? 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7, forever. It's going to go to infinity. I love it. Is there a sequence where you add up all the numbers, all infinite number of numbers, and it comes out to something that's not infinity? E? How do you mean E?
Number E.
What about it?
It's the sum of an infinite series that, there are an infinite number of factorials, but they're inverse, so.
Well, E, it comes from the integral, blah, 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 blah.
Yeah, it's also 1 over.
It's
1
the limit. Be careful, it's the limit of 1 plus 1 over n to the n. Not the sum of them.
Okay.
You with me?
Yeah.
Well, I like what you're thinking. But that probably everybody else, what the hell, stuff. Here's a really simple one here. You ready? What's 1 divided by 9? If you do that in the calculator, what do you get? And it makes sense, because you guys know what 1/3 is, right? What's 1/3 is a decimal? How do you get, and 1/3 is 3/9, right? And that's 0.333. How do I get to 1/9 from 3/9? I divide it by 3. So you get point. Right? Now watch this. You ready? That, I'm telling you that is the answer to my question. If you add 0.1 to 0.01 to 0.001 forever, what do you get? You get 1/9. Which is definitely a little bit less than infinity. So when I ask the question, normally people freak the hell out because you think if you have an infinite list of numbers and you add them, how the hell can you get anything other than infinity? There's a ton of ways.
Because there are a lot of things that result in infinite numbers.
As long as they're doing what? Yeah. Notice what has to happen. The limit has to be not just getting smaller, but the limit has to be 0. If your numbers that you're adding up, now be careful. That doesn't mean that it'll actually come out to be a nice number. But that is the first constraint. In order to have a chance for this to be something that's not infinity, then every single element has to be going to 0. I mean, not every single one, but eventually they have to go to 0. You guys kind of with me here? A little tight? No, it's just gone beyond. It's going to blow your minds. This is obviously a little beyond our talk. But I like to introduce this now because it's a subject you can kind of latch onto. Yeah.
Is that like where you kind of saying you're saying that as n approximately 1, is that what you're asking? Or you're
Yes. So part of this is isn't this 1/10 and this is 100? This is 1,000, right? So what is this? This series is going to be 1/10 to the n. Is that cool? So obviously, as n gets really, really big, this whole thing goes to 0, and because it does. When I add them all up, it has a chance to be not infinity.
Oh, it's like the convergers or divergers.
You look like that. Yeah, I didn't want to necessarily use that language. Yes, convergent or divergent. And that's something you'll talk about in calculus. Cool. Which sounds like some of you guys have at least seen some of already, which is always good. Alright, that's enough for today. We'll get back into sigma notation. Next time we'll have the quiz for a second.